Right, so hello, it's April 28th, and today the main theme is going to be combinatorics. And here are the reminders. First, we're going to have the take-home midterm this Wednesday, or the day after tomorrow. So, reminder. And also the last homework assignment is due then. And I'll hand this out on Wednesday. You'll have until Friday to finish it. So it's just a take-home thing. The length and the difficulty will be similar to that of a typical homework assignment. Okay? The only difference will be that it will be more comprehensive throughout the whole course rather than just for 1 week. And the other thing is you get more points for doing well on the midterm than you do for a single homework assignment. Guess this is 1 and 2. And then 3 questions. 4 combinatorics. Part 1. Okay, so before I start with combinatorics, are there any questions? Are you sure? Okay. So, as usual, there's a PDF and a worksheet posted here. And here we go. So, how many people have taken a course in sort of discrete math or combinatorics or something like that? So, a lot of people have taken a course, about half of you have taken a course in that sort of topic. Combinatorics it's a part of mathematics that has a lot of overlaps with computer science and probability and a lot of other areas. And it's really about, for the most part, understanding properties of finite sets, counting things, finding optimal elements of certain sets, optimal colorings of graphs, that sort of thing. So it's about studying discrete objects. Like, for example, this hypercube, viewed as a graph. And what we're going to do for the next couple of days, let me remind you by showing you the schedule. So far what we've done is some background on computing with Sage. And then we started with algebraic computing, which is the second part of the course, and talked about groups, rings, fields, prime numbers, and a little bit of number theory, distributed factorization, and some cryptography. Then we talked about matrix algebra and linear algebra. And now we're going to talk about combinatorics and then graph theory. That's for the rest of this week. So this week will be very much about discrete mathematics. One possible issue that might come up with a whole bunch of the topics that are coming up is that I'm a number theorist, and you might secretly notice that everything I talk about will turn into number theory if I'm not careful. So just don't make too much fun of me for that. I'll try to keep things actually about the stated topics. So here's a sense of the sort of combinatorics that are in Sage. There are really 3 main programs in Sage that involve combinatorics that are included as part of the Sage distribution. One is called Symmetrica. Another is called Network X, which is mainly for graph theory, which is a part of combinatorics. And GAP, which is mainly a group theory package, but one of its missions is computation with combinatorial structures. So it does do a number of things related to combinatorics. Also, there's a group led by Nicholas Thierry, who have worked very hard for quite a long time to implement a huge amount of combinatorics, especially related to algebraic combinatorics, in a system called MuPad. And they have, for the most part, decided to move over to Sage as of a couple of months ago, and they've been working hard to re-implement a lot of the functionality in MuPad Combinatorica in Sage, since they really, really like what Python has to offer and so on. And MuPad is closed source and expensive, and that's been a problem for them as a research group. So There was also a recent Sage Days conference, which I'll show you the website for. So if you go to wiki.sagemath.org, there's a list of websites for each Sage workshop. And Sage Day 7 was focused on combinatorics. And I guess that was the quote, because there was a lot of late night coding that went on. But if you look at the schedule and so on, you can see that there were quite a few talks about combinatorics in Sage, not in Sage, related to Sage, and so on. And you might notice that these 3 talks are all by UW grad students. So, and then that's a UCSD grad student professor. So here's some more talks during the second day. So the 10 o'clock talk is about this research group that works on algebraic combinatorics and implementing tons and tons of combinatorics for really quite almost a decade, and how they're thinking about or now moving over to Sage. And there's some discussion of representation theory by Dan Buff, who's a professor at Stanford, and then Emily here gave a talk on graph theory and so on. So you might want to look at some of these talks to get a deeper sense of combinatorics in Sage. And not only are slides available, but there's video right here for each of the talks. Though unfortunately, I've failed to upload this to Google Video, evidently, or even name the videos. But they're all there, so you can kind of just match them up. Let's take a quick look at each of these packages. So Symmetrica this is a web page for Symmetrica. It does a lot of different combinatorial computations involving everything from Schur polynomials to Young tableau to symmetric functions, and then a bunch of different representation theory type things. And it's really it's a fairly large, tightly coded C program. And it's very, very fast at what it does. I think it was a tremendous amount of work for the author to write, and it's, I think, been under development for, since the late 1990s. So my first sort of interaction with it was when I visited Dan Bump, who was on sabbatical at Reed College. And he, so he's a Stanford professor who's written a lot of computer code and also written many huge books on representation theory and large papers in number theory. And he was really excited about, or telling me about a Mathematica program he had written for computing products, computing the Schur product, which doesn't matter what that is, but it's some sort of product that comes up in combinatorics. And I tried using Sage to do the same calculation. Sage directly wraps Symmetrica, and it was literally thousands and thousands of times faster than his Mathematica program. Got the same answers, but it was way, way, way faster. So Symmetrica is very powerful and fast at some things, and does a lot of things that are really of interest to people in combinatorics. And behind the scenes, many things in Sage are really wrappers around Symmetrica. At least many specific combinatorics things are. So whenever Symmetrica gets better and faster, Sage also gets better. And there was recently a new release of Symmetrica. It was kind of weird. I think it was version 0 point something, and then suddenly version 2.0. And it went from taking about 20 seconds to build to over 5 minutes. So it was really a huge leap. NetworkX is for graph theory, and I'll say more about it when we talk about graph theory on Friday. And I'll kind of skip that for now. And then GAP, which does really a lot more than just combinatorics in Sage. This is an open source program for really computational discrete algebra and group theory. It's been around since the late 1980s, so it's been in development quite a long time. The lead developer of GAP, Steve Linton, gave a talk here in the Combinatorics seminar a couple of weeks ago. So there's a lot in here that's relevant to combinatorics. If you look at how some of the functions are implemented that I'll show you in a minute, they're implemented using GAP in some cases. So here's GAP. There's lots and lots of documentation and so on. So here's a list of mathematical capabilities. I think GAP really started in the mid-'80s as kind of almost an ideological counterpart to Magma. the guy Joachim de Buesser, who started GAP, really didn't like the way Magma was being sold and closed, but at the same time building a lot in the work of other mathematicians. So he started GAP. Actually, it was really a counterpart to Cayley, which is the predecessor to Magma. But it got a lot of funding from Germany in the 80s and the 90s, and then it eventually moved to England, where it is now, or Scotland, I guess. But there's a lot of people all over the world that work on GAP. So it's GAP. So these are three things, but there's also a huge amount of new code in Sage that was written specifically for combinatorics. And you can find that code primarily in the, if you go into the Sage distribution, which is right here, and go develop Sage combinat. That's the subdirectory, combinat. Then you see all of these files. And these files implement combinatorics functionality. And there's, I don't know, probably, I don't know how many people actively working on developing this code, but it's a lot. I don't know, Robert, would you have any sort of estimate for the number of people working on this? There's Mike, Dan, Nick.
Maybe a dozen or more.
Yeah, probably a dozen people working on this code. And they actually have a separate mailing list, a separate group that puts together code, and then once it's all ready to go, they give us a huge patch, and then it gets merged in.
Actually, the post set people just get another patch. So it's like,
What?
the post set people just make their first patch. So it's like 4 more people.
Wow, okay. So there's the PustSet people, there's the MuPad Combinatorica people. We're all at MSRI in Berkeley this summer, or this quarter, etc. working on this. And then Mike Hansen. I think Mike Hansen's sort of he's the guy that's just starting grad school in San Diego. He's the guy that's sort of coordinating the whole effort and has done a huge amount of the work. Just to give you a sense of the size of this, just so I guess that's just to tell you that there's a lot of code here. So just, that's what we're done. Okay. So pure Python, there's 24,000 unique lines just in this directory. It's a lot of code. There's one very interesting file in here, Sloane functions, that implements a large number. How many people here have heard of Sloane's tables of integer sequences? Oh, very few people. Let me show you that website, by the way. Sloane's. This is an extremely important thing to know about if you do combinatorics. Huh, that's annoying. The first hit for Sloane's tables is the Sage documentation about our Sloane interface function. So don't go there yet. Go to Niels Sloane's homepage. Integer sequences. Okay, so this is an amazing website. You can just take any sequence of integers that come up in your research or whatever, type them in here, and it will check against this huge database of known integer sequences and find sequences that look like your sequence. So, anybody have a favorite sequence?
Tom's not famous.
Well, I'll do a really stupid one, I guess. I mean, the obvious stupid sequence that, of course, will impress nobody that it finds it. But, so, you put in a few prime numbers, it says the sequence of prime numbers. But it finds 188 total sequences, some of which are maybe related to the sequence of prime numbers, but aren't. So this one's related because it's the complement of the sequence of prime numbers, I guess. Or something, I don't know. Or it's just some sequence that happens to start out with prime numbers. And I guess it's not, what is it? It's home primes whose homeliness is 1. So that's what this says. But, I mean, it's pretty amazing. You can just type in a sequence and then get 11431? 34. So Bernoulli numbers, apparently. Or something related to Bernoulli numbers. Zeta, that's interesting. So there's a formula for those numbers in terms of Bernoulli numbers, given right there. And is the next term 496?
Sorry, put a 2 before the 4.
1, 2, 4?
1, 1, 2, 4.
Ah. I'm sorry, but the terms do not match anything in the table.
Okay.
1, 1, 2, 4, 34. What is that supposed to be?
It's supposed to be the number of
Oh, well, it's not, because it would be in this. It would be in the. I mean, are you sure it's 2 1s at the beginning?
Yeah.
Maybe it's based differently without the empty graph or something. Nope.
No, I thought it was 34. Don't
Don't mind
mind me.
you. Okay. In any case, you kind of get the feeling. So this is an amazingly useful web page, because often you find some numbers somehow and you have no idea where they come from and you want to understand them better. So you type them in here and then you flip through 20 different possible sequences that begin with those numbers and you find some pattern. So let's see, going back to this file, there's an implementation of a large number of the functions from Sloane's tables in Sage. So if you go, for example, sloane.tab, you'll get a list of different Sloane sequences. I don't know, for example, that one. And then if you go like this, well, it's an exciting sequence, the 0 sequence. So maybe another more exciting sequence, Euler's Toshin function. And then you type, then you get out, the 10th term. So there's a lot of these implemented.
You omit a number of them, or?
That just gives the nth term in the sequence.
You omit a lot of the Sloane?
Yeah, it does not have every single Sloane sequence implemented. There are 100,000 sequences, and here you have like 150 sequences. Most of them are there because they're in some way interesting, and it's interesting to give an algorithm to actually compute them. There's some Sloane sequences where computing the next term could take years, or we don't even have an algorithm to do it. So there it's not so interesting to code it in Sage because it would just be a lookup table and then impossible. But it's not every single sequence. And it's something that somebody could add to at any moment, which would be nice. So that's one thing that's in Sage, is a nice implementation of a bunch of Sloane functions. Okay, so the first thing I'll show you after Sloane is combinatorial functions. There's a bunch of different functions that are related to combinatorics in Sage. Many of them are listed in the combinatorics section of the Sage reference manual. So let me show you how to find that. So if you go to the Sage reference manual, this very, very large document with dozens of chapters, one of the chapters is called Combinatorics, chapter 18. And you can see the different sections. This gives you, in fact, a pretty quick overview of the sort of combinatorics that's in Sage. In other words, there's a lot of different things in here. So there are implementations of combinatorial functions. There's the stuff for computing some of the Sloane functions. And the Sloane thing, despite it only being about 150 functions, the actual code files are massive. And it was really a huge amount of work to write that. Jaap Spies, he's a Dutch mathematician who's retired. He wrote the Sloane stuff. He did combinatorics as a researcher for a long time. Then he retired, and now he spends half of his time on his yacht sailing around the world, and the other half of his time implementing things in Sage. So you would only be so lucky to do that when you read that. So he implemented section 18.2. Then there's Bell numbers. So in fact, there's an interesting history there. I think Nick Alexander wrote a very, very optimized implementation of computing Bell numbers. There's a lot of different numbers in combinatorics that count some sort of thing. And that's just an example. Things that involve signed matrices. And then there's lots and lots of other things, like listing all combinations of certain objects with certain properties, etc. And there's some pretty technical stuff with all kinds of fun names like necklaces and stuff like that. So I'll show you combinatorial functions. So these are various things like Stirling numbers, Fibonacci numbers, Bernoulli numbers, and so on. And in some cases, I think it can easily be that there could be a much faster way to compute one of the numbers that's here. But in several cases, the implementation here is the fastest in the world. So it kind of varies a lot. But this says, in parentheses in some cases, it says what system computes it. And often when no system is listed, that means Sage is doing it, it's going to be very fast. I don't know, maybe the Euler number it's probably silly to do that in Maxima, and it might be possible to implement something that does that way more quickly. I mean, you could say that about any particular thing here. So a possible source of projects would be to look systematically over these combinatorial functions and see if any of them are not optimal. Or optimal means faster than any other program out there, and then fix them to be faster. But we've done this repeatedly, so it's certainly possible. And I'll show you some examples. So, back to this. I mean, it turns out often these combinatorial functions, they have a definition that shows that you could compute them just by doing operations with integers, but it turns out there's some clever analytic function that converges to the same number as the combinatorial function. So for example, I'll show you something like that in a minute, but there are a number of cases like this, like computing the number of partitions of an integer, which is a number of ways of well, I'll show you that in a minute, but that's an example where there's an infinite series that converges to the thing, and you could compute the number of partitions in some like completely straightforward manner, just involving integer arithmetic, or you could use an infinite series and then compute it to sufficient precision and truncate and then see what you get. And the two answers will agree. And if you do the calculation using the infinite series, as soon as the number you want to compute gets large, that can be vastly faster than the integer arithmetic version of the calculation. So there's a lot of opportunities for speeding things up using that. Okay, so here's a combinatorial function factorial. It counts the number of ways of permuting n objects. That's one of the most basic combinatorial functions that you might think of. This is an example of something that's quite fast, as I've pointed out many times before. Like 1,000,000 factorial takes only 2 seconds to compute, despite the answer taking, the actual decimal expansion will take longer. The interesting thing in computing factorial is that if you compute 1 times 2 times 3 times 4 times 5 in order, it will take vastly longer than if you compute 2 times n and 3 times n minus 1 and 4 times n minus 2, and then multiply those together in a sort of tree structure. So interestingly, what happens is even though when you multiply together in the non-obvious way, you end up doing more multiplication operations, the total time is far less as n goes to infinity. And the reason is because when you do 3 times 4 times 5 times 6, what happens at each step is you have a big number, the product so far, times a tiny number. Whereas if you do a sort of balanced multiplication, at each step you have numbers that are roughly the same size. And even though the total number of multiplications is more, the amount of time spent is far, far less. The reason is because if you multiply a massive number times a tiny number, then there's not really much you can do to do that more quickly than the obvious grade school arithmetic method. Whereas if you multiply two numbers of roughly the same size, there's an absolutely massive amount of tricks that people spend years and years and years thinking about optimizing for multiplying those two numbers quickly. And it just turns out it's vastly better to do the multiplication that way. So that's the reason that factorial is so quick, is because it uses a clever way of multiplying the numbers together.
Do you know what kind of tests you've done to make sure the numbers are close enough together to use these tricks?
Well, I mean, it's pretty obvious when you write down the algorithm for factorial that they're all about the same size.
No, I mean,
but if you did an arbitrary product,
yeah,
then
or there's some rule of thumb that they have
so,
to be somewhere. I mean,
that's a good question. I don't know.
You know how many limbs you have in a big one?
Sure, you know how big a number is. I don't know. I mean, it's almost always better to do a balanced product if you can. And I think Sage.
If you could say precisely how close they have to be together.
So the Sage product command, by default, if you do prod and then give a list of things, by default it does some sort of balanced tree-like multiplication. So in fact, if you just do, multiply the numbers from, if you do this, it's actually not much worse than GMP's built-in factorial. Let's see. I'm a little scared to try something really big because that's not so bad actually. Let's try that. So the top one is the optimized factorial in the GMP library. The second one is the completely generic product implementation in Sage, which just takes any random list at all of Sage objects and then multiplies them all together. But it does it using a tree, so that the products are more balanced. It's just, I mean, if you're going to choose something at random and not even look at what you're multiplying together, a tree works much better. Let's just, for fun, try doing the same product but without recursing at all. So k equals 1. I don't think I want to go up to 10 to the 6. Let's do this first. Okay, so let's try 10 to the 5th. Just the naive multiply without using some sort of tree structure. 3.69 seconds, exactly the same thing. We're multiplying all the same numbers together. Takes much, much less time. So the speed up just in this one example is 3.65 divided by 0.19. So almost 20 times faster. It's really, really important that you think about how you're multiplying numbers together. By the way, if you look at Magma version 2.12 and earlier, their factorial command literally just went 1 times 2 times, well, times 3 times 4 times 5. But their prod command, which in Magma is denoted and star, so that'll multiply the numbers up to 10 as soon as it starts up a copy of Magma. Their product command did the balanced multiplies. So in fact, if you did factorial of 10 to the 6 in Magma, it would take a long, long time. Whereas if you did and star and then made the list of numbers up to 10 to the 6, it would be very, very fast in comparison. So it's kind of funny. We did point this out to them and they fixed it. So now it's not so bad. Okay, another number that comes up a lot in combinatorics is the Bernoulli numbers. They're introduced by a Bernoulli, I'm not going to say which, in around 1700. I don't know exactly when. And I'll say some more about them in a minute, because not only are they really central in combinatorics, but they also play a big role in number theory. So they're something I'm very interested in. So Sage can compute Bernoulli numbers. And these Bernoulli numbers, they're rational numbers. Their definition's pretty simple, and I'll give it in a minute. Sage can compute Bell numbers, Catalan numbers. I don't even know what a Catalan number is, and I don't think the help is too useful. Let's see. Oh, no, here's the definition of a Catalan number. The nth Catalan number. There are actually a number of these combinatorial functions where the help doesn't really define the thing for you. So here's an example. Notice here it just says return the nth Bell number. And then the number of ways to partition a set of n elements. And somehow it's a slightly unsatisfactory docstring, because it would be nice if it maybe said what it did or how it worked. Also, looking at the source code, it does just use gap. Okay, strange. I'm just puzzled because I could have sworn there was a very fast implementation of Bell numbers that was much better than gaps in Sage. So maybe I'm misremembering slightly. Euler numbers. So this wraps something. I don't even know what an Euler number is, but there they are. It's Euler numbers. Fibonacci numbers. Everybody knows what those are. Let's see how Sage does that. So if I just do double question mark, I hit the tab key. You can see that Sage calls, by default, Perry's Fibonacci command. And that's how it computes Fibonacci numbers. So I have no idea if this is a very good implementation or not. I don't know if, I mean, the numbers get so big that, well, it doesn't take long. So I don't know if there's some way to do Fibonacci numbers more quickly, but maybe. So Stirling numbers, number of partitions. So I mentioned that before, number of partitions. So if you have an integer, there are various ways of writing it as a sum of smaller positive integers. And those are called the partitions of the integer. So this is a list of all the partitions of the integer 5. And notice you do allow repetitions when you write it as a sum. But the order doesn't matter. So in all cases, they're just sorted. So a basic sort of combinatorial problem is count how many ways you can partition an integer as a sum of smaller integers. And this number of partitions function comes up a lot in all kinds of areas of mathematics. So I overheard somebody say that it's one of the most important functions in mathematics. So
for the Fibonacci numbers, you could certainly solve the difference equation.
yeah.
And you get an expression that's a simple exponential and plug into that. Surely it would be faster than doing an iteration. So they probably don't know that there's that formula for Fibonacci numbers.
But this is extremely fast, so maybe they do know. I'm sure the authors of Perry know about that formula.
Okay, so you think they plug into that formula then?
If that's the fastest way.
Well,
I don't know. There's a lot of surprises when it
but
comes
surely
to
you wouldn't do it by iteration.
I doubt they're doing it by iteration, given the speed of less than a second for the 10 millionth one. But I don't know. And there are many surprises when it comes to computing combinatorial functions. Yes, Igor?
But for the factorial function,
Yes.
Isn't there a trick with Sturm's approximation?
If you only want an approximation.
Yeah, but like...
This is computing the factorial on the nose with literally every digit of precision right. So like this is really computing over 1 million digits right there. Way more than 1 million digits. Like if you look at this thing, every single decimal digit is right. And it's a very big number then. If you just want the number of digits, there's a formula of Sturm that will give you the number of digits of n. So like the floor of log of n, for example. But it's literally computing 5,565,709 digits on the nose, every single one of them. If you just wanted to know this number, 5565709, the number of digits, or the first few digits of the factorial, so you wanted to say a floating point approximation to factorial, then you're absolutely right. There's a formula of Sturm that can do that very quickly, which is very useful to know about. It's with many surprising properties. It's like this infinite series that doesn't really converge, but you can still use it for computation. So here's some more. This just allows you to see partitions of other integers. So partitions of 7, etc. Partitions of 11. There's a lot of partitions of an integer, as you can see. So I'm going to tell you just a little more about computing the number of partitions. So let's try computing the number of partitions of 10 million. So as you can see already, the answer is going to be big, because this is just the number of partitions of the number 11. So number of partitions of 12. So number of partitions of 10 million is going to be quite large. And Sage computes that in 1/4 of a second. And the actual number of partitions is it's a number with 3,515 digits. So it's extremely big. This is a plot of the number of partitions function, which just gives you a sense that it grows very quickly. So, is there any question in anybody's mind about what the number of partitions of an integer is? It's just a number of ways of writing it, so some of these things. So the reason that this got fast was kind of interesting. What happened was I was going through the Mathematica tutorial, and there's like a little Mathematica tour, and on page 6 they say, Mathematica can compute the number of partitions of, I think it was 10 to the 9th. So it was an absolutely massive number, so a billion. And they said it could do it in seconds. It didn't say how many seconds, but it just said seconds. And they said this is a frontier calculation in number theory. So I thought, well, Sage is supposed to be a program for number theory. Maybe I should try that in Sage. And of course, it just died. And in fact, I remembered recently on the mailing list there had been subtle bugs uncovered in Perry's implementation of the number of partitions function on 64-bit Linux boxes. So that was an issue. And I remember that those bugs came up around 10,000, and already there it was getting too slow. So Perry was just not going to do this calculation. Gap, which was the other alternative, was much, much slower than Perry. Perry was our much faster alternative to Gap, which we unfortunately had to turn off because it had subtle bugs. So I just mentioned this on the Sage Develop mailing list, and then a thread suddenly happened with about 60 different messages. And within a week, a grad student at University of Michigan named John Bobber, who does combinatorics, and he's actually one of the people now contributing a lot to graph theory and combinatorics in Sage. implemented from scratch this function for computing the number of partitions. And at least on my laptop, it's about twice as fast as Mathematica. So it's quite good. And the source code itself is interesting. It's in this file right here. If you go to the root of your Sage directory and go into comnat partitions_c.cc, you can see it. It's based on a paper from 1938. Let's see, so partitions_c.cc. Oops, sorry. Sorry, I haven't got the right name yet. So here's this program. He got some help from various people, and it's a C++ program. Let me just shrink this some more. His comments are really out there. Yeah, so you can see the comments. He comments a lot, which is nice. Some of the comments, though, are scary. Let's see. Where's that one name? Yeah, I found this to be kind of amusing. Extensive trial and errors found 3 to be the smallest value that doesn't seem to produce any wrong answers for some particular function that appears deeply embedded in the code. Thus, to be safe, we use, and then he uses more than 3, but some precision bound that comes up at some point. So if you look at the Perry source code, so this is some good Sage source code. You see massive amounts of comments, explanations, and magic constants, and so on. If you look at some software, I won't make any comments about closed source software, because you can't look at it, but Perry will be similar except with far fewer comments, and here it would have something like question mark, magic constant, question mark. Possibly in English if you're lucky, which is unfortunate, but that's what you often get with some systems. So this is very, very good as far as comments goes, I think. But it's basically something that uses GMP and MPFR and all these systems for doing arbitrary precision arithmetic. But at the end of the day, it uses almost completely a paper from 1938 by Hans Rademacher, and then various tricks and very careful bounds to determine how much precision you need in certain infinite series to compute this exact function. Take the function, the number of partitions, takes it as input an integer and outputs an integer, but in order to implement anything that's any good at computing it, you need all kinds of floating point arithmetic to arbitrary precision, and you need to understand how to bound infinite sums and so on. That's really what goes into it. One of the fundamental flaws in the GAP program, is that they don't have any native support for floating point arithmetic at all. It's just like they decided it wasn't necessary because they're for computational or combinatorial algebra and group theory. Who needs floating point numbers? So, for example, their implementation of number of partitions is ludicrously slow because they don't, think about things from this point of view. I think it's really kind of silly. There's a ton of things that appear to be at their surface purely combinatorial, but they're intermediate steps along the way that really should be done in a numerical manner. Just like with linear algebra, which I was explaining a couple of days ago, that if you want to multiply matrices with integer entries or entries in a finite field, it's often best to turn the problem into matrix multiplication with floating point entries. Do matrix multiplication there and then get back the correct result. In computation, you do that sort of trick a lot. And if you try to exclude it from your toolkit, then you'll be second best. Okay, so any questions about the number of partitions function before I move on? Okay. Next, I'm going to tell you a little bit about Bernoulli numbers. And so the plan is to show you some things about Bernoulli numbers, and then we're going to start on Friday with combinatorial structures, which are very useful if you want to write, you want to come up with situations for TV shows. So you take all the characters of the TV show and then choose different ways of combining them together to make a cool scene. Okay, so mainly what I'll talk about now is Bernoulli numbers. That's really the rest of today. So here's the definition. And since it's actually a very easy definition, but if you forget it, you won't understand anything I'm saying, I'll just write it down on the blackboard. So on the left-hand side, I just wrote down a function of x that you would see in a calculus course. you could imagine taking its Taylor expansion, and that would be an infinite power series. On the right-hand side, I write down an infinite power series whose nth coefficient is bn over n factorial, where the sum goes from 0 to infinity. E to the x minus 1 doesn't have a big 0. It has a 0 of order 1, so you don't need any negative terms here. So this equality defines a sequence B sub n of rational numbers. And they're, again, defined by the above formula. And a kind of standard problem in mathematics, which is the one that inspired the initial definition of Bernoulli numbers, where they came from, and that's actually the first problem I ever thought about when I was 10, is to compute the sum of the first n integers. So there's a nice formula for this, n plus 1 over 2. There's a story about Gauss computing this sum for n up to 100 instantaneously while all of his classmates sat there and do it by hand. So for example, if n is 100, and you get 5,050. You get it kind of instantly. But what if, instead of summing just the first n integers, you want the kth powers of the first n integers? So back in the 16 and 1700s, people worked extraordinarily hard to come up with generalizations of this formula at the top. And they came up with specific formulas for different values of k, like for the squares, the cubes, and so on. And again, this has sort of a combinatorial feel because you're counting powers of sums of numbers. It also has a very number theoretic feel. It's very, but I think it counts as combinatorics. So, so it turns out that there's a simple closed form formula for this sum for any value of k in terms of Bernoulli numbers. Let me show you that formula. Skipping over this. So here it is. I have unfortunately used different notation on this slide than over there. I've written this sum. I used r for the exponent instead of k, but you can follow along at home. So on the right-hand side, you have a finite sum of powers of n, where the coefficients are Bernoulli numbers and binomial coefficients. The quick way to encode this in your mind is that if you want to generalize this formula right here, the answer is a polynomial in n, but the coefficients are given as a simple expression involving a Bernoulli number. That's what this says. Okay? So the generalization of this formula is basically a polynomial of degree k plus 1 in n, involving Bernoulli numbers. By the way, here's an impressive statement that Bernoulli makes, just using this. So by the way, for the sums of the squares, here's the formula. At the end of the day, you end up with 2n cubed plus 3n squared plus n over 6. And you get that just by taking this formula I gave up there of Bernoulli and computing the first couple of Bernoulli numbers using that definition over there. There's one little caveat. You have to use a half instead of minus a half for b sub 1 for everything to work out correctly. But aside from that one funny thing, this is what you get. Now here's a funny quote of Bernoulli. I have found in less than a quarter of an hour that the 10th powers of the first 1,000 numbers, beginning from 1, added together, equal that number with really a lot of digits. He did that by hand in like 1700. It's pretty impressive. So, maybe Gauss computed the sum of the integers up to 100 quickly, but he computed the sum of the 10th powers of the integers raised to up to 1,000 in less than an hour. So just to check his work, here's what he did. The sum of the 10th powers of the integers up to 1,000. And indeed, it's the number that he gives up there. There it is. And he goes on to say, from which it is apparent how useless should be judged the work of Ismail, Boleal, whose name of course you don't remember, because you've never seen it before probably, recorded in the thick volume of his Arithmetica Infinitorum, where all he accomplishes is to show that with immense labor, he can sum the first 6 powers, part of what we have done in a single page. So this is where Bernoulli numbers were introduced first into mathematics, hundreds and hundreds of years ago. And it's really impressive that by hand, Bernoulli could compute that. I mean, in less than an hour. Wow.
I don't think I could ever do that.
I know. Imagine if that was the in-class midterm. You have, really did that 300 years ago. You can do it. Yeah. E.
Back then, they weren't going to check his work, right? So.
Well, in the book he gave the formulas, so somebody else could just spend an hour and, I guess, check it. And anyways, it's in a published book, so he could be worried about posterity. He's right, though.
Yeah.
That's the even more impressive thing. Nobody. But it. I think he. Well, he gives exactly how he does it. He says he uses this. So in fact, all he has to do is compute, I guess, 10 Bernoulli numbers, which isn't that hard. It's just computing that series to 10 places. And then he has to write down these binomial coefficients and do some, I mean, literally the number of arithmetic operations he does isn't that big. So it's quite reasonable, in fact, that he did this by hand and got it right. Given that he's one of the greatest people at, arithmetic by hand that's ever lived. But, I mean, literally he is. So there he is. Well, at least that's A. Bernoulli. Might be the same one. I don't know. Another interesting connection between Bernoulli numbers and things you might have seen before that has a lot to do with combinatorics. Okay, this has nothing to do with combinatorics. This has a lot to do with number theory, but the sum of the squares of the integers, the sum of the squares of the inverses of integers is pi squared over 6. It's kind of a standard formula everybody knows about. And it generalizes. So this is, right here, this is zeta of 2. The Riemann zeta function is the sum of 1 over n to the power of the number you plug in there. And for every even integer, zeta of 2k is 2 to the 2k minus 1 times pi to the 2k divided by 2k factorial times the Bernoulli number 2k, e2k. So basically, the way to generalize that formula right there is to replace the 2 by 2k and then throw in a Bernoulli number and a factorial and a power of 2. So, for example, so if you just drag the slider, it gives some of the 4th powers. And the right-hand side is just being computed using the Bernoulli number formula that I typed in. So that's how this formula generalizes. Let's see. And just like with number of partitions, Sage is quite fast at computing Bernoulli numbers. I have to get rid of the semicolon. It doesn't actually compute it. Well, no, it already computed it. I know. So the Bernoulli number 2010, in Sage it takes 0.75, and in Mathematica it's 1.74. So again, it's actually very similar, the timing difference between Mathematica for Bernoulli numbers and for number of partitions. And the underlying algorithm is, I think in both cases, basically the same. It's just being a little more careful about bounds. Bernoulli numbers are huge, by the way, once you get going. So, like Bernoulli, I don't know, 100, it's already getting quite big. Bernoulli 1000, oops, for odd numbers they're all 0. But there's Bernoulli 1000 Bernoulli number. So it's pretty big. There's one sentence. If you want to compute all the numbers, all the Bernoulli numbers, modulo a prime number p, you can do that extraordinarily quickly. In 0.12 seconds, this computed all the Bernoulli numbers up to 20,011 modulo 20,011. And there's an algorithm of Joe Buehler that's kind of had a big impact on number theory over the years that's implemented it. All right, so I'll see you on Wednesday where you'll have the take-home midterm, and we'll talk about combinatorial structures. So counting all the subsets with certain properties and so on.